Anyway, I don't want to discuss as Professor Abhik told me that already you have been looking at grand potential, Kim Suzuki and all, and you have already become some mini experts in this areas. So I don't want to go inside all this detail. I'll just show you one or two demonstrations and we will go. And only thing is, and we have Achyut and Pushkar who are actively on the CUDA part of it. And previously, Shaurav used to work on it, the previous development. But now we have also gone further. We have now introduced various ways to effectively run the multi GPU solver. So, and I am sure that Achyut will share some of these uh, important the important advancements that we have made in our solver. Okay, so anyway, so as you can see that we have this KKS module and you have seen that. So I'll not go into any detail of it. I'll just tell you that it can do simulations of solidification. It can do simulations of precipitation and it uses NVIDIA GPUs, typically V100, A100. Even we have tested for P100, but below that we have seen some issues. So I hope that we do not have H100 yet, but I hope that that will also be supported. So, and also please note that we do communications between GPUs using MPI. This is CUDA aware MPI. And also there is one very important point. So that some improvements that Achyut has recently made. So all those things Achyut will share. And we also have elastic interactions in the CUFFT MP. And currently, I don't know how fast it is, but I hope that it is now going to be pretty fast with the improvement that he has. So as I was telling you, CUFFT MP integration is there, and we have also the elastic, we calculate elastic interactions. And one very important thing that I'll try to do today is to just show you how we do elastic interactions calculations, how we do the calculations for elastic interactions. Or so today I'll go at least I'll go through the elastic driving force. How do we calculate in homogeneous systems, and you can easily follow how it is done for inhomogeneous systems. In inhomogeneous systems, we do something like perturbation. Once the inhomogeneous elastic solver by the end of this month or so, after the testing means testing is done, the development and testing is being done, and I hope that within 1 or 2 months we will be able to release the inhomogeneous elastic solver also. Right, so I don't want to go much in the detail, but I can just show you the capabilities. One movie, for example, is this coarsening in nickel aluminum molybdenum system, which is already there in the MicroSim repository. You can basically run this simulation, and you can download and run this simulation. You can take the input file, and you can also see the movie. The movie is also kept there. So another is this solidification simulation, that also for the aluminum zinc. And as you know that we have also written the MicroSim paper where these examples were also used for benchmarking across various solves. So there's a few things that were not there. For example, this is an earlier version of the code where we used it for basically, as you can see here, you have formed these plates, and these plates are forming in this in an elastically anisotropic system where precipitation has happened, and these precipitates are growing. Initially they were cuboidal, and at the later stages they became plate-like. Right, and this is also a very beautiful solid, a very beautiful dendrite that was. So now I don't want to go into this multi-phase, multi-component KKS model, but I want you to focus on this F elastic term, and also to focus on how we calculate the elastic stress effects, right? So I don't want to go into this right now. I don't want to go into this right now. I want to basically refer to one of the PDF files where I showed everything in detail, and I'll share the PDF file with you guys. So, so this is where the entire Fourier space elastic solver comes from, and it is basically given by Khachaturian. So if you look at Khachaturian's book, structural transformation, theory of structural transformations in solids. It's a classic textbook. And go to chapter 7. You will see most of it, but means I have tried to be slightly means I have tried to simplify it a little bit. And so I'll now and this is done. This particular tutorial, or this particular tutorial I have written with some Tata Steel engineers in mind. They came for this MicroSim training, so that time I gave them this explanation, and I hope that this will help you in understanding how this solver is now currently executed in our module. So as you can see, in this theory, that first of all, the model that I am talking about here uses a homogeneous modulus approximation. Okay, and you can actually go with an expansion of the Green's function. You can go to inhomogeneous systems, but currently we are talking about homogeneous systems. Okay, and where we are modeling elastic energy that arises due to lattice misfit. That is the lattice. There is a mismatch in lattice parameters, which but again although there is a mismatch in lattice parameters, the mismatch is not big enough, so the lattice planes and directions are continuous. And as a result, we have something called coherent systems. Coherent systems or interfaces are coherent. Coherent interfaces means that you do not have dangled bonds or broken bonds, but you have some stretching of bonds at the interface. Not much, and the stretching happens because of the lattice parameter mismatch. And also one very important thing, since there is no dangled bond, so as a result, the interfacial energy of these systems generally tends to be the interfacial energy between the precipitate and the matrix tend to be very small. Okay, so but there is this lattice mismatch. This is because of the precipitate phase has a different lattice parameter than the matrix phase. Now, in these cases, what happens is you give rise to, so the system gives rise to elastic strains, right? And it gives rise to an elastic driving force. So we will show you quickly, means we'll try to show you quickly how basically this is done. Okay, so and please note that this Khachaturian's theory has come from another theory, that is Eshelby's thought experiment, or Eshelby's Gedanken, and that basically are given in Eshelby's classic papers. So the detailed derivation here, I have given a detailed derivation of Khachaturian's theory. But if you want to go into Eshelby's ideas, then you have to look at his papers. Okay, so but the idea is very, very simple, and I'll just show you how this idea came into being, and that idea was the foundation for how Khachaturian treated the elastic energy. And the most important thing that I want to tell you is that the theory or the method stems from how to write the elastic energy in Fourier space. We generally know how to write the elastic energy in real space, but when you have a inclusion in a matrix, but the way the Khachaturian's idea is to write it in Fourier space. As soon as we write it in Fourier space, actually for homogeneous modulus approximation, we basically solve the elastic problem, at least the constant part. Okay, the Green's function we solve even before the time loop. That's why it becomes quite fast, the homogeneous modulus approximation. And please note that the shape change with size that you see in your real microstructures is all because of the misfit strain. The inhomogeneity just adds second order effect. Obviously, the second order effect becomes important when you want to study something like rafting. But when you want to look at shape change with size, the arrangement of the precipitates, their alignment, then basically homogeneous modulus approximation is good enough. Okay, so what we are going to show is how an inclusions misfit induces the elastic strain and stress fields, and then also the hypothetical steps to insert a misfitting inclusion. So this is something that again I took from Khachaturian's book, and this is nothing but, see, you have a homogeneous matrix to start with, as you can see here in this region. Now what you have done is you have taken out some, that's why it's a thought experiment. You have basically created a hole by taking out this circular regions, and these circular regions, what you are doing is that there is some phase transformation that has happened. And as a result of phase transformation, these circular regions have undergone some change in lattice parameter, and you can basically see that this change, because of this change in lattice parameter, the shapes also have become, and the misfit can be anisotropic also. So maybe the circular regions became slightly more ellipsoidal. Right now, these include these are basically now in a stress-free state, they are transforming. Right now, they are transforming, and these holes are there. Now, what you have to do, if you have to basically, in this step, you have these transformed precipitates. Now, if you have to put them back, then you have to give surface stresses. And this is exactly what this Gedanken does. And again, for this particular step, again, you can write that you have to add the surface stresses, and then you can only put them in this hole. And once you do that, the system has stresses in it, but this system has stresses in it. Now the system, because you have to put stresses there. Now the system has stresses in it, but then the stresses go away because system wants to become stress free. And then you finally get the stress free constrained system where you have this misfitting precipitates in a matrix, right? And this is the final state where you basically get the finally you write the elastic energy fall. Right? These are all the steps in which your stress and strain, the stress state or the strain state in the system is going to be different. Right? And now finally, when you come here, this is the problem, and this is where you want to tell what is the stress inside the precipitate, what is the stress inside the matrix, what is the strain inside the precipitate, what is the strain inside the matrix, and also what happens at the interface. So all of these come into being when you basically look at this inclusion process. Now, this is where the steps are. I don't want to basically go back, so I have already described. So just I'll share these slides with you. You can read through it, and then it becomes easy for you to follow. So eigenstrain or stress-free transmission strain basically is some way of telling that, say, for example, if there is a phase transmission that has happened, or say some thermal expansion that has happened, that remember eigenstrain is studied well in mechanical engineering in the form of thermal strain. So these are all stress-free strain. Here it is basically due to lattice parameter mismatch due to phase transmissions, but it can also happen due to some thermal strain because of some unequal thermal expansion of the precipitate and the matrix. Right? So this eigenstrain, the most important thing is that it's stress-free, and we use a superscript of 0 to identify the eigenstrain. Eigenstrain by itself can be elastic in nature. However, note that in the overall scheme of things, the eigenstrain you can think of, say, a plastic deformation, and you can actually tell that the plastic strain is like an eigenstrain. Only thing in that case, the plastic strain has another constitutive or a flow rule. Right? In this case, the eigenstrain that I am talking about has no flow rule. Right? So this has happened just because of the transmission where the precipitate has a different lattice parameter than the has different lattice parameters than the matrix. And as you can see, at different along x, along y, and along z in the unit cell, you can have different changes in lattice parameters, and as a result, you can have anisotropic eigenstrain. So once you have done it, what you tell and what Kachaturian invoked is something called a shape function. And he basically wrote this form where he's telling that this is the eigenstrain for phase P, which has a constant part, as you can see here. And then it is related to something called a shape function theta PR. This shape function is nothing but the phase field that you consider to distinguish between the phases. Right? This shape function is nothing but the phase field that you use to distinguish between the phases. So, and obviously, as you can see, that if you have eigenstrain, you may have eigenstrain, but finally, what you basically, in absence of body force, you have to make sure that if you think of mechanical equilibrium, the sum of forces have to be 0. Now, sum of forces means surface forces as well as body forces. Surface forces are the traction forces, which basically is related to stress, because stress always acts on surface. And then there is also body force, and the body force can be gravitational, electromagnetic. But if you assume if you ignore the body forces here because of gravity and all, then basically what you get back is a divergence of stress tensor to be 0, and divergence of stress is nothing but, if you think of divergence of stress in a volumetric sense, then you can use the divergence theorem, and it is nothing but sigma dot n, and n is the normal to the normal to the surface, and basically sigma dot n is nothing but force. So sum of forces equal to 0. So that this is given in this equation, del sigma ij del xj equal to 0, and this is the equation that we want to solve. Okay, and obviously, if we are using elastic regime, then the stress is related to strain via Hooke's law, right? A linear relation, which basically tells you sigma ij equals to Cij KL, epsilon KL elastic, right? Epsilon KL elastic. Now, if you think of that, you have this elastic strain, and as a result, you have stress, and the proportionality is nothing but a Cij KL, and that came immediately. You can see from the tensor relation that you have Ij here, you have KL here, so it should be a fourth rank tensor, right? So elastic strain is dimensionless, and Cij KL has the same unit of stress, and stress is force per unit area, so it has a unit of Pascal. So, and the total strain, as you can see, because this system already has eigenstrain, is elastic strain plus the eigenstrain, right? The total strain is elastic strain plus eigenstrain. So the stress is only related to the elastic strain, and therefore stress is Cij KL epsilon KL minus epsilon KL naught. Okay, and then obviously you can use isotropic. Cij KL can be, it's a fourth rank tensor. It describes the material stiffness, right? That means resistance to elastic deformation. And yeah, hello. Yeah, Vic. I can
Yes,
speed
sir,
up.
please.
No,
No,
is there
yeah,
any?
continue.
Okay, okay. Yeah. So it can be isotropic, it can be cubic. In your MicroSim solver, you will see that you can take tetragonal or rhombic, different types of symmetries, right? So in general, if you use symmetric, if you use isotropic, then you will basically see two constants, these Lames constants, and these are, that means you require only two coefficients to describe, so two independent coefficients to describe the material stiffness, right? So, and there is also a contraction that we use. You can refer to NI and you can understand, and this contraction is used by Voigt notation, where we basically, because sigma ij equals to sigma ji and epsilon ij equals to epsilon ji, and these comes from the energy invariance and also from the couple, right? This comes from the couple, the conservation of angular momentum. So basically, in such cases, once you have done that, then what you will see is that Cij KL can also be written as a 6 by 6 matrix. Okay, sigma can be written as a 6 by 1 vector. That means that's a stress vector which has 6 components, and then there can be a strain vector which has 6 components, because stress and strain are symmetric tensors, right? And Cij KL also is a symmetric tensor. It has these different symmetries, like the energy symmetry, the stress symmetry, and strain symmetry. As a result, ultimately, you can basically have the 6 by 6 form. In that, again, because of Cij equals to Cji, you will have 21 constants. And out of these 21 constants, if you do further symmetry operations because of isotropy, you will finally end up with 2 constants for isotropic systems. For cubic systems, you will have 3 constants. And all these things are encoded in the MicroSim solver. Right, so you will have, and in very important that when you write these constants, you will have one parameter called the Zener anisotropy parameter. Okay, and this is called Voigt notation, as I was telling you. And this Zener anisotropy parameter is related to C44, which is related to the shear modulus. And then you have C11 and C12, right? And this 2C44 by C11 minus C12 in case of isotropic systems is 1. So Az is 1 for isotropic, but Az can be greater than 1 or less than 1 for anisotropic systems. In BCC systems, many a times you may see AZ is less than 1. That is, some particular directions are elastically softer. That means the elastic energy in certain directions are softer, like 1, 1, 1 directions. On the other hand, for FCC, it is found that the 1, 0, 0 directions are the elastically soft directions. That means the elastic energy cost is less along these directions, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And there you will see that AZ is greater than 1. Okay, now one very important thing that I have to tell you is that some of these quantities vary spatially. For example, eigenstrain, as you have seen, that eigenstrain has a constant part, and then there is a theta p, which is basically your phase field. And the phase field does vary spatially, therefore the eigenstrain also varies spatially, right? And there comes the idea of, so since it varies spatially, it does not remain a very easy equation to solve, right? As a result, what we use, and that is what Khachaturian's contribution is, that if you can write the elastic energy in the Fourier space, then basically you can use that to make the to have a solver which is a very much simplified, much faster or much quicker solver. In fact, some of these solutions he found out analytically, particularly for the ellipsoidal inclusions, right? And obviously, Eshelby himself has done that. So, but Khachaturian showed, or Khachaturian's theory enabled us to use those solutions very quickly or adapt them to the phase field model. So it became quite fast and quite popular. So as you know, all of you have already learned Fourier transform, and you know I don't have to give any definition. Sometimes in physicists use 1 by root 2 pi also in front of it, or you use my e to the power minus 2 pi I k dot r. That is used. That is the convention I think used by FFTW. And this I am using minus for the forward one, and for the inverse one I will use plus. But that's again another convention. Right? For inverse, for example, this is how the inverse is defined for any function. So one important thing I have to tell you, that once you know the sigma and you know the strain, you also use a small strain assumption, and we define something called displacement with the small strain assumption, right? So this part, so as you know, the displacement is the gradient in displacement is related to the strain, right? The strain is basically the symmetric part of the deformation gradient, right? Del ui del xj plus del uj del xi 1 by 2 in front, right? So basically, one very important thing I have to tell you, if you have to solve this equation sigma ij means del sigma ij del xj equal to 0 in terms of stress or in terms of strain, then what you have to solve is compatibility conditions. And it becomes very difficult because you have like 81 compatibility conditions. It becomes you can solve using Airy stress functions and stuff. But if as soon as your situation becomes complex, like microstructural evolution, in such cases, it becomes very difficult to solve in terms of stress or strain. You solve in terms of displacement. And the advantage is that once you write everything in terms of displacement, your compatibility conditions are already satisfied. You don't have to solve any additional compatibility conditions. So that is the beauty of, writing everything in form of displacement. And that's what we do. So this is what we have done here. So goal is to solve this. Goal is to solve this with the eigenstrain del sigma ij del xj equal to 0. You are able to see my cursor, no? Are you able to see my cursor?
Yes,
so
yes.
You're not able to, huh?
No, it's visible. It's visible.
Okay. So you have this real space equation. Now see, the problem in this real space equation is that you have the second derivatives, you have another derivative. So it becomes a bit cumbrous, right? In some way, because you have so many derivatives. You have a second order derivative, and you have also a first order derivative. So in Fourier space, that is one of the beauties of Fourier transform, that the Fourier transform of a derivative of a function is the Fourier transform of a function itself weighted with the reciprocal space vector. That's the idea. So that is what is exploited when you use spectral method. So I take a function, I take its derivative. The derivative is nothing but the Fourier transform. The Fourier transform, the derivative is nothing but the Fourier transform of the function itself, weighted by the root minus one, that is the imaginary number, and the k space vector. Okay, as a result, this equation now, as you can see here, this del 2 uk del xj del xl becomes nothing but Cij Now xj and xl, when I do a Fourier transform, so remember this is a second derivative, right? So second derivative, so in general the rule is I is the imaginary number, whole to the power n. So if I take the nth derivative of a function, if I take the nth derivative of function and the nth derivative exists, means the function is differentiable. So then the relation is very simply the Fourier transform of the nth derivative of the function is basically equal to I, which is the imaginary number root minus 1, times k whole to the power n. K is the magnitude of the vector, and ik whole to the power n, and f tilde. And f tilde is the Fourier transform of the function itself. So function is f, and I am doing del nf del f del some del f del x, del nf del xn, means del nf means nth derivative, nth order derivative of the function. Then it becomes ik whole to the power n f tilde. So that means any whatever be the order of the differentiation, if you basically know how to use Fourier, if your function is periodic, then you are done. If your function is periodic, provided your function is periodic. Okay, for non-periodic also you use cosine transforms and sine transforms, but if your function is periodic, nothing like it, right? And it immediately it becomes very easy for you to solve. So you have Cij. Now you have this del xj and del xl, which basically goes to Fourier space with this kj and kl, and uk, that's the function, which is a function of, was a function of r in real space, has now becomes a function of k, which is the k vector in the reciprocal space, with a tilde sign. And then on this side, you also have the eigenstrain, which is a function of r. Now this is the Fourier transform of the eigenstrain, which is a function of k. And then you have the Cijkl, and there is a kj. Now look at this. This term is there, this Cijkl, kjkl. Immediately you can see, if you know tensor, and I'm pretty sure that you know tensors very well, that you can see that j and L are repeated indices or dummy indices. So basically, what are the free indices here? I and K. And right, so this part, just this part, Cijkl, kjkl, is nothing but a second rank tensor. And this tensor we call as the inverse of the green function. That's the idea. And if I do this as the inverse, as you know, if I have A inverse F equals to something, that A inverse, I have to take the other side. So I'll just invert it. And therefore, this becomes A times A inverse. And here A times A inverse is identity. And identity multiplied with anything is the same, right? The same function itself. And here you just have the inverse of the, so you get the inverse of Green's function here. And here you basically, when you take it this side, then what you are multiplying with is the Green's function. So the idea is very simple. So this Green's function is defined here. So as you can see here, this is the Green's function, right? So we have a Green's function, say GIMK, and this Green's function is multiplying this entire right hand side, right? And what you get is the solution in one step. The solution in one step. And the Green's function, as you can see, for isotropic, you can write in terms of lambda and mu, and in terms of n, where n is k by mod k, and you can basically compute that. So you think of this, you are getting the displacement solution for a homogeneous system in one step, right? You get the displacement solution in one step. Okay, you are not taking any derivative, you are not expanding with finite difference or finite element or finite volume. It becomes really, really efficient. Obviously, one caveat is that it has to be periodic. So now once you have got that, you have the small strain approximation. I want to quickly go through it because I do not want to bore you guys. So what I am trying to say is that once you do all this, you can basically write the the total strain, again in the small strain approximation. That's why there is no, so remember, we are using small strain. If you use finite strain, then there is a multiplicative term. So this solver also will become iterative. Currently, this solver with homogeneous modulus approximation is not iterative. So you get the total strain here. And then you can basically, once you substitute the Green's function solution, you basically get the total strain tensor solution in terms of the displacement solution. So displacement is the fundamental solution. And then you get the elastic strain also in Fourier space. So you get all the fields. Remember, that's what we are looking at. So once you get all the fields, you can actually calculate the energy also in Fourier space, and you can calculate the driving force in Fourier space. And that is exactly what we are doing. Okay, so but very important thing that I have to tell you, that since you are using periodic boundary conditions, how will you apply stresses or strain? So it becomes very difficult, right? So there is a concept that was given by the French group of Moulinex and Souquet, and then Michel further enhanced it, and it is used in crystal plasticity also. And that concept is called homogenization concept. In the homogenization concept, what we tell is that whatever be my RVE, we can always think that in that RVE, there is this local strain or the periodic strain, which is because of the periodicity in the displacement. But there is also an overall constant strain, and that strain is called homogeneous strain, where we are assuming the entire RV to be homogeneous. Now, you understand. So that part, that homogeneous strain is basically, or uniform strain is across the material, whatever be the microstructure in the material. So that is basically called the homogeneous strain. And that homogeneous strain can be mapped to anything like applied strain or applied stress. Okay, and this is very, very important, because if you don't do that, if you don't calculate the homogeneous strain, often what you are doing is you are when you are particularly applying Fourier-based solvers, you are basically artificially constraining the system. That is, the internal stress in the system, the overall stress in the system goes on increasing. However, if you want to make sure that your system remains stress-free, if you want to make sure that your system remains stress-free, what you have to calculate now is this additional strain called the homogeneous strain. So what happened is, so the total strain that Khachaturian had was now divided into homogeneous strain and this heterogeneous or periodic strain. And now once you have that, you use a condition that the heterogeneous strain, the integral of the heterogeneous strain or the integral of the periodic strain over the volume goes to 0. And that is the condition that we use to calculate the homogeneous strain. Once you have calculated this homogeneous strain every time, you are ensuring that your system is stress-free, right? So, and in the case of homogeneous modulus approximation, you can actually see, and very beautifully you will see, that it is nothing but the average of the eigenstrain. The homogeneous strain comes out to be the average of the eigenstrain. So when you calculate, you will basically find that the average of the eigenstrain is what is the homogeneous strain for a system where you have homogeneous modulus approximation. Right. So now the elastic energy, as you know, I don't want to now go further. I want to quickly show you that if you have this elastic energy density expression, then you already have the solutions in terms of displacement, strain, and if you know strain, if you know displacement, you also know stresses. So once you know that and you put it all together, then what happens is the elastic energy in Fourier space has this very interesting term which is called the interaction kernel, and you have this theta p tilde and theta star q, and this comes from this Parseval's relation. And you will understand one very beautiful thing here. This is nothing but, in your case, this is nothing but the phase field. For example, it can be eta p square, it can be eta p or phi p. For example, in MicroSim we don't use eta, we use phi. Right, so phi is your phase field, but it's just a convention, and you can use phi here, and phi tilde is what you are basically multiplying. And so once you do that, one very important thing that I just wanted to tell you is, I don't want to go into this detail. Okay, you can look at it in your spare time. I will share this thing, and then what it comes out to be is here is the final result that comes. This is the final result that comes. Okay, I don't want to go into the final result of the elastic part and then the variation part. So what is the most important part that comes out is this BPQ theta P. Okay, so this BPQ, that once you get the interaction term in Fourier space, which you are calculating outside the time loop. Please note, you are calculating outside the time loop, and the theta P is your phase field. And this phase field is only thing that you are basically having inside the time loop. And then it becomes very fast. So you have this, yeah, so I don't want to go into the detail of it. So you combine both of them and you find this one, the del F elastic del theta I is BPQ theta P or BPI theta P, and you have the homogeneous term, and then this is the del theta I del T. This is the Allen-Kahn equation or the time-dependent Ginzburg-Landau equation. And basically, in your F, you already have the F elastic, so you have the driving force, right? Del F del theta I is the driving force, right? Basically, it is nothing but the driving force with respect to the eigenstrain, and eigenstrain is related to theta or the phase field, and therefore this is del F del theta. So once you have done that, so I don't want to, you can go through it quickly because Abhik told that only part that you want to understand is already you have understood all the nuances of the KK's model, grand potential model and all. So the only part that you would be very interested in is this how Khachaturian's microelasticity theory comes into phase field and how we calculate the elastic interactions. So this part you please go through, you please go through all of this. And if you have any question, feel free to write to me and I will be happy to answer. Okay, and I can also take up some questions. Yeah, so this is the idea that we use in our model. And now going back to the part here, that where we have this delta C and all, this is something not yet implemented in our means it is implemented, means all of us, everyone in MicroSim has this inhomogeneous lastic solver. However, it is not yet in the main branch. So in the main branch, we will include it very soon. And then we can actually discuss about the inhomogeneity also. So thank you very much for your attention. Hi. I just rushed through because I saw that I am almost talking for an hour.
Take question.
I'll take questions.
Sir, yeah, please.
Or
I can repeat this. Yeah, 1 second. Please.
yes. Yeah, very nice talk, Professor Bhattacharya. So I'm Supriyo.
Hi, very nice.
Hi, yes.
Hi.
So since you're using Fourier transforms, I have some question. So
Yes.
apart from its periodic, so there are issues with Gibbs oscillation, right?
Yes, I know.
So how much stiffness contrast you can actually capture in this model between the precipitate and the matrix?
Okay, so let me tell you that the stiffness contrast, definitely you will tell that, see, there are various techniques to do that. The iterative perturbation method is very bad in that case, because as soon as Gibbs phenomenon comes, the ringing happens, and if the ringing happens, you cannot really use it. However, there are also many sophisticated solvers, for example, equivalent eigenstrain based solvers, okay, like the Khachaturian has one theory where you basically take a virtual eigenstrain and basically evolve it. There, the contrast does not matter. You can take infinite contrast. It does not ring. It does not show any ringing. However, in the Fourier space also, I have one very important. See, our phase field models are diffuse interface models. As long as ours is a diffuse interface model, and we have at least resolved with 8 to 10 grid points the interface, okay, that ringing phenomenon does not really affect our simulations. It is very, very critical when you want to do this in crystal plasticity, because in crystal plasticity you are dealing with a sharp interface and you want to get the jump condition. And then when you are doing this, and it's a sharp interface, right? It's an atomically sharp 0 width interface. As a result, if you are not careful, you can actually end up with a lot of gives this ringing type of phenomenon, which basically makes your solver inaccurate. You can completely agree. Yeah.
So because of diffuse interface, you are saying means you don't see them at all. Means so you can
yes. No. Yes. So we do not see them at all. If we have, please note that the diffuse interface has to be resolved with at least 8 to 10 grid points. Then you do not see them at all.
Yes, okay. And the second question is, so this is a small strain formulation. So can you
Right.
think of a finite strain also formulation here to have
Yes,
larger
we would be happy
eigenstrain?
to. We would be happy to discuss with you, Professor.
Mhm.
So, and one very important thing I want to tell you is that when even with homogeneous modulus approximation, as soon as you have a quadratic term, as you know, then basically your solution will become iterative. You cannot now, because you have a quadratic term, right? Fourier transform of um, means if I have a product of two functions, I cannot just tell the Fourier transform is the product of two. It's not a Fourier. It's it's not the in Fourier space. It is not the Fourier transform of two functions, and then I multiply. It becomes a convolution. As a result, we require We require a convolution kernel. As a result, we require an iterative process, right? So, but it can be
Yes.
done. Actually, people have shown that at least for finite strains, the French groups have shown that it can be done quite nicely using Fourier spectral method. Right, but it has to be an iterative process. Means you have to basically you have to use a small strain approximation. Then you are basically using some sort of a reference state, and then
Yes.
based on that reference state you iterate. Yeah, I think you know. Yeah.
Mhm.
So yeah, so that is how it can be solved. But it will be a very nice thing to do, because most of the Martin-Zedek transformation problems are finite strain
Yes.
problems. Yes.
And the twinning also, so you can do
Yes,
twinning.
absolutely.
Yes.
I completely agree that those are not small strain problems. Those
Yes.
you cannot use small strain. And yeah, this is to be a very nice and interesting thing to do. Definitely.
Okay. Thank you. So
Thank
yes.
you. Thank you. Thank you.
Any other questions? Any other questions? I have, but this seems different. I'll ask you. So no questions. Other questions? No. No more. So, yes, sir. So there are no questions.
Okay.
So if you